We left part 1 of this EVU mini course by asking the question, why can't we build higher capacitor, cheaper EV batteries? The answer is that we can, but the technology is complex. So what's the battery capacity and cost challenge? Inside an EV, there is a limited space and a limited geometry in which we can place a battery. Therefore, we need to design and build batteries with higher energy density per cubic inch to overcome the geometric constraints. But there are also weight constraints. Every additional pound that an electric motor must move forward reduces the EV range for a given battery technology. Finally, there are other technological metrics. Each of these must be considered as new battery chemistries are developed. The metrics can be represented using a radar diagram shown on the right of your screen that provides what we call a footprint for the battery. Let's consider each of the metrics separately. The first technological metric we'll consider for EV batteries is specific energy. Specific energy is the capacity of the battery, the amount of energy it can deliver until it is depleted. Specific energy is measured in energy output per unit weight, for example, kilowatt hours per kilogram. Because the EV competes directly with ICE vehicles, the ultimate challenge is to achieve the specific energy of gasoline. Gas delivers 13 kilowatt hours per kilogram, over 100 times more energy density than a lithium-ion battery. It's highly unlikely that batteries will ever achieve the specific energy of gasoline. So for now, the goal is to double or even triple the specific energy of EV batteries. The second technological metric is cost. Battery cost is the primary reason why current EV buyers pay a price premium for EVs. Cost is a function of the manufacturing cost for battery cells, the individual batteries that are the building blocks for an EV battery, the cost of the battery management system and its related subsystems, thermal management systems that control battery temperature, a safety system that is designed to recognize any safety problems and protect the integrity of the battery and the safety of the customer, the driver, and a power management system that controls power flow into and out of the battery. Support hardware that incorporates power electronics, wiring harnesses, and pack housing are also part of the overall cost. The chart on the right of the screen provides a typical cost breakdown for an EV battery pack. The battery cells themselves represent 50% of the overall battery cost, with electronics, control systems, management systems, and other business costs representing the other half. The third technological metric is battery lifespan. Every battery degrades as the number of charging cycles grows. A battery's lifespan is the number of charging cycles that a battery can accommodate before losing 20+% of its capacity. It's a function of temperature. Battery performance and lifespan degrades as temperatures go above 86 degrees Fahrenheit. Charging protocol. Whether charging regularly occurs with a fully depleted battery or one that has significant capacity left, and the degree to which the battery capacity is charged to its limit. Today, battery costs are high. Therefore, lifespan is a major concern because the cost of battery replacement for an EV would be significant. The fourth technological metric is performance. An EV battery must provide the power needed when needed without fail. Performance is a somewhat vague term that addresses the ability of the battery to meet its power and recharging requirements regardless of its environment. This includes the ability to operate effectively in various climates. For example, extreme temperatures can impact battery capacity by 20 or even 30%. In fairness, it should be noted that extreme temperatures can also affect the range of ICE vehicles, sometimes significantly. Finally, performance also alludes to the time required to achieve a full charge, with higher performing battery taking less time for a full charge. The fifth technological metric is safety, normally considered in the context of battery fires or other reactions that might endanger the driver or passengers. There are well over 150,000 vehicle fires in the U.S. every year, with the unfortunate reality of approximately 350 deaths and almost 2,000 serious injuries. 99.99% occur in ICE vehicles. To date, there have been very few verified safety issues with EV batteries and/or EVs in general. But the media seems obsessed with any fire that might be even remotely related to an EV battery. The most celebrated cases occurred with 3 different Tesla Model S vehicles that had fires during 2013, its first full year on the market. The media reported these events as if car fires were rare. They are not. Here's a comment on these incidents from MIT Technology Review. In 2 cases, the cars ran over large metal objects at highway speed. The third car hit a concrete wall. No one was hurt. A warning system allowed the drivers to pull the car over and get out before smoke started coming from a battery pack. And the design of the battery slowed the spread of the fire, which never made it into the passenger compartments. However, public perception is reality, and for that reason, a sophisticated safety subsystem and robust battery enclosures are mandatory elements of the battery management system. The safety system ensures that there's no thermal overload and also controls runaway charging or overall runaway power operation. The last technological metric is specific power, sometimes referred to as the power-to-weight ratio. Specific power is the amount of power delivered per kilogram for any object that produces power as output. For ICE vehicles, specific power often refers to the power produced by an internal combustion engine versus the weight of that engine. For EVs, it refers to the power produced by the battery versus the weight of the battery. Batteries with high specific power can discharge electricity rapidly in powerful bursts, with the observable benefit that EV batteries with high specific power allow their vehicles to accelerate rapidly. The design trade-off is that high specific power increases the cost per kilowatt hour of storage capacity. The Boston Consulting Group used the 6 battery metrics we just discussed to create footprints for 5 different lithium-ion chemistries. A quick scan of the footprints indicates that lithium titanate batteries, based on advanced nanotech, offer the low cost and reasonable specific power, a very long lifespan and good performance, particularly their ability to recharge quickly, but relatively poor specific energy, meaning that battery capacity would suffer. A detailed discussion of the footprint for each of these battery chemistries is beyond the scope of this mini course, but if you have interest, follow the link provided to learn more.